So a relation is some kind of rule or equation or mapping that relates to variables. And this is an example. I say this is a relation because if you know a little bit of information about x, it's going to also allow you to relate that to some kind of knowledge about what y is. Just as an example, if I know that x was 0, then y has to be either 5 or negative 5. So maybe I could even map these together like this. And you know, if x is 3, that forces y to be either 4 or negative 4. And if I said y is equal to 4, well then x has to be either 3 or it could be negative 3. And in fact, if x is negative 3, it could also have a y value of negative 4 and so on. So it's not exactly like a one-to-one function where I tell you an x value and you tell me a y value. But a relation is kind of a more general idea where there's just some kind of connection or some kind of relation between the two variables. Okay. That said, a function is a special kind of relation. We've been dealing with functions already. And a function is just a relation where every input value is only mapped to one possible output value. Not like the example I just showed you. That wasn't a function. But in a function, every x value maps to only one y value. If we use the word independent is synonymous with input. So if your independent variable is x, your input variable is x. Likewise, dependent, that just means the same thing as output. So there's nothing tricky there. Just new vocabulary words. In exercise 1, it says, determine whether each of the following are functions with y as the output and x as the input. And if you get this kind of question, solve for y. If I wanted to take this first relation and solve for y, I could subtract 1 from both sides and add y squared to both sides to get that equation. And then, in order to solve for y, I would take the square root of both sides. But like we've discussed before, if you have an equation and you take the square root of both sides of your equation, you have to throw in a little plus or minus sign to remind you that if you take the positive number squared, it's the positive number. If you also take the negative square root squared, it's still positive. So both of those are valid. The question is asking, is this a function? In other words, is this one of those relations where every x value is mapped to only one y value? And the answer is no. Because if you tell me an x value, and we calculate x squared minus 1, and then we take the square root, and then we say, well, this could be positive that number or negative that number, I've got two y values that correspond to the one x value you gave me. And so this is not a function. This is an example of a relation that's just not a function. Again, I can tell because y is either equal to positive this number or y is equal to negative that number. But functions only get one y value. This one, on the other hand, if I were to solve for y, I would subtract x squared from both sides. And then I would divide both sides by 2. And this is a function. Because in this situation, you tell me an x value, There's only one possible y value that corresponds to your x value. What about this next one and the middle left side? Is this going to end up as a function? I guess we gotta solve for y in order to check, see how it goes. I think solving for y means we could factor out an x that looks like the greatest common factor here. On the left side of the equation, I get 1 minus y cubed. And then I could divide both sides by x. Then I would think about, what if I subtracted 25 over x from both sides, and I add y cubed to both sides. And lastly, to solve for y, I would want to take the cube root of both sides. And that's my formula.
Wait, so you don't have to add plus or minus cube and minus?
Yeah, you're right. Well, this is the rule. If it's an even number, like a square root, or a fourth root, or a sixth root, or an eighth root, then you do have to throw in a plus or minus sign. Because if you have a negative number raised to the fourth power, it becomes positive, because you end up multiplying through 4 negative signs. Anytime you've got an even number, you have to throw in the plus or minus sign. But if you have an odd number, like 3 or 5 or 7, odd numbers don't need a plus or minus sign. Because negative 2 cubed is negative 8, and positive 2 cubed is positive 8, and they retain their plus or minus sign identity for odd powers. And so that square root principle we talked about applies to square roots, fourth roots, sixth roots, eighth roots, and so on. It does not apply for cube roots. It doesn't apply for fifth roots. It doesn't apply for seventh roots. And so this is a function.
So given that rule, can you just look at the y's exponent?
Exactly. Yeah. You are on top of the ball today. You could just look at the y exponent, and if it's y raised to the 2 power, then the answer is no. Because eventually you're going to have to take the square root of both sides to solve for y. And so that's going to end up with a plus or minus sign. That means you get 2 output values, and that means it's not a function. What about this one? Yeah. This is just the function y equals 2 to the power x plus 5. So that's a function. And what about this one over here? No. Because again, you saw the y raised to the 4th power. You know that 4 is an even number. And so when I take the 4th root, I have to throw in my little plus or minus sign. That reminds me, no matter what the x value is, there's like a positive y value corresponding to the x value and a negative one. Because of that even number root principle. Yeah. Okay. So sometimes you write down an equation and it's just a relation. And sometimes you write down an equation and it's actually a function. Functions just mean you get one output value and only one output value for every input value. The next thing today is called the vertical line test. And this is a visual way to check if your relation is a function or not. And this is what the vertical line test says. It says, if you've got a curve in the xy plane that looks like this, and you imagine drawing a vertical line through it, and that vertical line intersects with your curve more than once, then it's not a function. In this case, it passes through 3 times, and so that's not a function. On the other hand, if your curve looks something like this, anywhere I place a vertical line only passes through this curve once, and so this is a function. That's the idea with the vertical line test. I've got some equations we can put into Desmos so that you can see if they are functions or not. But the idea is, on a test, I might just give you the picture. I might not actually tell you what the formula is. And if I gave you this picture and you had no idea what the formula is, what you want to think about is you want to think about that vertical line test. And so you imagine any kind of vertical line, like this one, and if you can find a vertical line that passes through my curve more than once, excuse me, that tells us this is not a function. Okay, 2 times, not a function. And again, the reason that this works, maybe you understand already, but a vertical line only has one x value, right? Right now the x value is 7. Everywhere on this blue line, the x value is 7. So what I'm saying is for this one x value, this red function actually has 2 corresponding y values. One of them is like +1, and the other one's looking like -1. You know? If you've got 2 y values for the same x value, then it's not a function. So you can say no, but y cubed equals x minus 1. That curve does look like a function. Because again, no matter where I place this vertical line, it only passes through the curve 1 time. So that's good, it passes the vertical line test. What if I had y squared equals x squared minus 4? And I know that you can tell from the y squared that this isn't a function, but again, on a test, you might not have the formula. Maybe you only have the picture. And you can tell from the picture because, well, you can find a vertical line that would pass through the curve twice. So that's not a function. And then if I do something like sine of x minus y equals 0, that curve, only looking at the picture, is that a function or not? Yeah, that's a function. Because it only goes through once, so it says it passes the vertical line test. Okay, so that will definitely be a test question. Do you have any questions or concerns about that? The next thing today is function notation. And so far, we've been writing functions that look like this, right? I say y equals some function of x. And what function notation actually does here is it looks a little bit different. It means the same thing, but it looks a little different. This part on the left side of the equation tells you my function's name is f. It gives you a name for your function. And then what happens right here, where I have parentheses x, this has a name. This is called the argument. And the argument tells you my input variable's name is x. So when I use function notation, I'm telling you this is the name of my function. This is what the input variable is going to look like. And the right side of the equation is still the rule that maps your inputs to your outputs. And if I read this out loud, what I actually say is the words f of x. So I would say f of x is equal to x squared plus 1. And the only point of possible confusion here is on the left side of the equation, it kind of looks like there's a variable f times a variable x, because when we multiply stuff, we just write things next to each other. You just have to use your context clues to say, you know what, that actually looks like function notation. It's not two things I'm multiplying together. It's just the way we write function notation. But it is a little bit, it could be a little bit confusing until you get used to it. Honestly, we would never really need to do this in an algebra class, except that it becomes important if you want to become an engineer, if you want to study calculus, if you want to learn computer programming. Those are all fields where function notation is everywhere and you've got to get used to it. But you'll see that Desmos is totally cool with function notation. Right? I could type in y equals x squared plus 1 in Desmos, like we always have been doing, or I could type in something like this. And it looks exactly the same. Same function, just two different ways of typing it in. And what's next is evaluate the function. And notice what I've done is I said, we're going to define my function to be f of x equals x squared minus 3x plus 5. That's the definition of what my function is. But what my question is asking next is, what is f of 2?
2x squared minus 3. 3 times 2 plus 5.
Yeah. If I replace the argument and change the x into 2, then I'm going to go through my whole function, and every place where I see an x, I'm going to replace it with a 2. And when I'm done simplifying, I say f of 2 is 3. All right, what if I say f of negative 3? Then I go back to my original function definition here in orange, only I replace all of the x's with negative 3. And when I'm done simplifying, I can say f of negative 3 is 23. What if I want f of x plus 1? Then again, I go back to my original function definition, and I replace all of the x's with x plus 1. That's 9 plus 9 plus 5. And then if you multiply, then you distribute, and you collect like terms, and you're done expanding and simplifying everything, this is going to be x squared plus 2x minus 3x plus 1 minus 3 plus 5, it'll be x squared minus x plus 3. And then if I have one more, we'll do f of negative x. Same thing. Go back to your original definition of what is f of x. And this time I replace the x with negative x. So I write negative x squared minus 3 times negative x plus 5. And when we simplify, we say f of negative x is x squared plus 3x plus 5. Does that make sense? Okay, so again, among the things that Desmos can do, you can also define a function like x squared minus 3x plus 5. And then, if I want to know what is f of negative 3, he'll tell you. Right? I don't suggest doing your homework this way, but if you're checking your answers to your homework, that's pretty neat. What if I wanted to check my answer to the part where I said f of x plus 1? Well, it's not going to tell me what the expanded form looks like, but it will give me the curve. It'll plot the curve for me. And then if I plot what I put down, right? So, messed up. There we go. So now if I typed out what I actually put down as my answer, and I also put in f of x plus 1, I can see that they're the same curve, so it must be the same function. So I must have gotten my answer right. That's a way to check the answer. Okay, next thing. Got a bunch of different, very small, very easy topics today, I think. This is called interval notation. And the way interval notation works is I say, here's my real number line. I'm going to put a few points down. And what if I want to represent the set of all numbers between negative 2, which is right here, and positive 3? How could I write down some symbols that represent all of these numbers together along my real number line? I want a set that includes 1/2 and negative 3/4 and negative 1.999999. And one way I could write this is I could write parentheses negative 2 comma 3. And this is the open interval. And it does not include negative 2 or 3, right? So if I write parentheses negative 2 comma 3, that's talking about every number, all infinitely many numbers that are situated on that number line between negative 2 and positive 3, but it doesn't include negative 2 and it doesn't include 3. It does include negative 1.99999, and it includes positive 2.99999, but it just doesn't include the very endmost points. That's what we call an open interval. If I draw square brackets, then now what I'm talking about is the closed interval. And it does include -2, and 3. So if I write square brackets, the square brackets tell you, hey, you need to include this endpoint. You need to include -2 and include +3 in this set of numbers. You can also get a little bit of a mix-up, right? Like I could do something like this, and that's allowed. That kind of notation would say include -2, but not 3. I will warn you about another point where students get confused. And the issue is that open intervals look exactly like coordinate pairs, right? This is the frustrating part. If I talk about a point on the xy plane, a point on the plane is going to have 2 coordinates. It has an x coordinate, comma, a y coordinate. And we use parentheses whenever we write a coordinate pair. So that's a little bit frustrating, is when you see this, you don't immediately know whether you're talking about a point in the plane or if you're talking about an interval along the x-axis, right? You just have to use context. Read the question, figure out what the question is asking, and if the question's asking for an interval, then this is interval notation. If the question is asking for a point, then this is a coordinate pair. That's the idea. It's frustrating. It'd be nice if there were different symbols, but...
Are these the ones on a number line? Like when you represent them on a number line, they either have like a colored in circle, like an arrow?
Oh, yeah.
That is the same thing?
Yeah, I know what you're saying. That's probably the same thing. So, let's talk about domain and range. The domain of a function is the set of all allowed input values. And in this context, we only care about real numbers. I know that earlier in the semester we were having a discussion about imaginary numbers and complex numbers, but now, whenever we discuss the domain and range, we're going to forget about that and we're only going to worry about real numbers. When I say allowed input values, I'm talking about what values of x make this function work. What values of x give a real number output. And then the range of a function is the set of all possible output values. So what I mean by that is, if you plug in every point from the domain, what kind of numbers are possible to get as an output from this function? So look at the first one, where I've got the square root of x. What is the domain of this function? So the domain is saying, what input values can I plug into the square root function that are going to give me real numbers as an output? Very good. Yeah. The way I answer the question is I write square bracket 0, comma, positive infinity. Because I can plug in 0 into the square root. The square root of 0 is 0. That's perfectly fine. I can also take the square root of any positive real number. And the square root of a positive real number is a positive real number. We're still good. I cannot put in a negative number, because if I take the square root of a negative number, that's an imaginary number output. And in this situation, I said, well, I only care about real numbers anytime we discuss domain and range. And so the domain is just restricted to this interval where I put a square bracket around the 0 because I want to include the 0. And this includes all of the positive reals. And so I put plus infinity as the endpoint. And anytime I use the infinity symbol, I always put a round parentheses around it on that side, because technically infinity is not a real number. and so we don't include it in our set of numbers. Okay, what about the range? What's the range of this function? Yeah, it would be the same. Very good. So if I plug in 0, the square root of 0 is 0. And if I plug in any other positive number from the domain, I get any positive number I want as an output, right? If I just choose the right input. So the domain and the range are the same for that function. Moving on. What would be the domain of x squared? I can plug in any real number I want. It doesn't matter if it's positive, if it's negative, if it's 0. All of the numbers are going to work here. What's the range? Is it possible for me to get a negative number output? Yeah, so the range here is 0 to plus infinity. I can only get positive numbers if I take a real number and square it. Okay, the next function is 1 over x. What's the domain? The domain is the set of all allowed x values. What x values am I allowed to use? And another way to think about this is, what x values am I not allowed to use? I'm allowed to use positive numbers, right? 1 divided by a positive number. I'm allowed to use negative numbers. I can do 1 divided by a negative number. But I cannot use 0. Yeah, so my domain needs to be written in such a way where I do not include 0. And this is how I write my answer. This is a funny symbol called union. It looks like a capital U for union. And what this is saying, in math notation is, I've got one interval in my domain that goes from negative infinity up to 0, but it's round parentheses, so I do not include 0. I've got another interval in my domain that goes from 0 to positive infinity. Once again, we're purposefully excluding the 0 with the round parentheses. And when I glue these together with the union symbol, I get all of the real numbers except not 0, which is good. So I can't have 0. What is my range of this function? What kind of output values can I get? Almost. There is one value that I cannot get from this function. 0. Yeah, so if I take 1 divided by a real number, I can never set that equal to 0. It's always 1 divided by something. It's always not 0. So 0 is the only number that does not show up in the range there. Next one. What is this domain? Yeah. The domain is everything from 5 to infinity. If I tried to plug in 4, that doesn't work, because 4 minus 5 is negative, and I don't want to take the square root of a negative number. It'll give me an imaginary number. But 5 to infinity works. And what would be the range here? 0 to infinity. Okay. the next function named g down here, what would be this domain?
Negative.
Yep, all real numbers are in the domain. What about the range?
0 to
If I were to get 0 as an output, what would be the input? What x value gives me a 0? So the smallest number I can get as the output of this function is actually 3. And the reason for that is because x squared can only go down to 0. You can't get a negative number out of x squared. And then at the end, I'm adding 3. So 0 plus 3 is 3. That's as low as excuse me. It's as low as we get. Okay, one more. This function, 1 over x minus 4, has what domain?
negative infinity to 0, u 0 to infinity.
That's what we had for 1 over x, but this time it's 1 over x minus 4. So what x value are we not allowed to have this time? 4? Yeah, positive 4 is the part that we can't have now. I can have 0, because if I plug in x equals 0, the output is just negative 1/4. But if I plug in x equals 4, then I've got 1 divided by 0, and that's no good. Okay, and almost done here. What's the range? What's the one number that I cannot get as an output?
Oh, 0.
0. Yeah. Once again, I've got 1 divided by something, and 1 divided by something can never ever be 0. So the range has to intentionally exclude 0. Do you have any questions about this kind of stuff? Everyone feels good about it?
So, oh, sorry.
Question? Yeah.
So anytime it's like we see the division, it's gonna be so the range is gonna say a union where zeros never an option.
Oh, gosh, that's a hard question. I mean, it's a good question. I'm glad you asked. But if I had this, now my range does include 0, because if I make x equal to 0, then this would be 0 divided by negative 4, and so I could get a 0 as part of my range. Just because you're dividing doesn't necessarily mean you can't get a 0. There's one number that's missing from the range here. Can anybody guess what it is? I know this is a super hard question. And we haven't ever done this before, so I don't blame you. But just in case anybody can think of it, what's the one number you can't get as an output from this function? So here's how I can test. I can say, what if 4 is my function's output? Then 4 is equal to x over x minus 4. And in that case, I get 4x, right? If I multiply both sides times x minus 4. 4x times, or sorry, 4x minus 16 is equal to x. And that means 3x is equal to 16. That means if I plug in x equals 16 thirds, well, 16 thirds minus 4 would be 16 thirds minus 12 thirds, so it would be 4 thirds in the denominator. And so I would get 16 thirds over 4 thirds. And then I want to multiply by the reciprocal, because dividing is the same thing as multiplying by the reciprocal. And then we cancel the 3's, and 16 over 4 is 4. So I actually can get 4 as an output if I use 16 thirds as the input. That's a good guess. But anyways, that's how you would check if you had a guess. Right? You could just replace the function output with the number 4. Any other guesses before I tell you? So I can't get 1. If I tried to get 1, that's what my equation would look like, right? Well, what if I multiply both sides of this equation by x minus 4? And I've got x minus 4 is equal to x. And, you know, you can think, is there any numbers x where x minus 4 is equal to the same number, right? 10 minus 4 is equal to 10, that doesn't work. 11 minus 4 is equal to 11, that doesn't work. This is never ever true for any number x. And so no x value fits this equation. And that's why 1 can't be an output. That's why 1 is excluded from the range here. 4 would be excluded from the domain, right? I can't have 4 minus 4 in the denominator. But 1 is the thing I can't get as an output. Maybe long division would help a little bit here. Sorry, we're going off on a tangent. I didn't even plan this as part of my lecture notes. But what if I rewrote this improper rational function as a proper rational function? I would write 1, you know, because I'm doing x divided by x minus 4. So 1 times x is x, and then minus 4, parentheses, subtract. My remainder is 4, so I would write plus 4 over x minus 4. That's the same function. It's just written in mixed form now. And you can tell, maybe from looking at this, that I can never get 1 as an output of this function, because no matter what I choose for x, this is 4 divided by something, so it's not 0. And something that's not 0 plus 1 has to be something that's not 1. I don't know. I'll try to make these fairly straightforward questions, and on a test, it's likely that this will be a multiple choice question too, right? So you can kind of eliminate answer choices and think about it that way. Okay, we're back on track. This one says, for each of the following functions, let's graph it and then use Desmos to tell what the domain and range is. Okay, so maybe there's a test question where I don't give you the formula. I don't give you the formula, I just give you the picture, and I expect you to tell me the domain and range based on the picture. So what if you don't see the formula? Pretend you don't see it. And if we don't look at this, what's the domain that you get from looking at the curve? Yeah. So domain is the set of allowed x values. And this curve has all kinds of x values starting with positive 6. What is the range of this curve? Yeah, perfect. The right way to write this is to start at negative infinity and go up to negative 1. because those are the y values I can get with this curve. It's everything below -1. And so without looking at the formula at all, right, pretend we didn't see the formula, we know the domain is 6 to infinity, and then the range is -infinity to -1. By the way, if you don't see the formula and you only see the picture, there's no way for you to tell whether the endpoint is included. Like, you don't know if the 6 is included, you don't know if the -1 is included. And so I'm not going to be nitpicky on a test. If it's a multiple choice question, I'm not going to give you like both answers but with different brackets, you know? I'm not going to try to trick you. I will make sure that it doesn't matter. You know, the fact that you can't tell from the picture. It doesn't matter whether this is going to be a square bracket or a round bracket. I'm not going to try to trip you up like that. Okay, next one says we've got 1 over x plus 3 times x minus 1. So this is what it looks like. What would my domain be? If you didn't see the formula, right? Pretend you're blind. You don't see this over here. But you see the picture. Can you tell from the picture what your domain is going to be?
-infinity to -3 union, -3 to 1 union, and then 1 to positive infinity.
Yeah. I can tell from the picture that my function is not well defined at -3. I've got this pole. It's not well defined at +1. Again, I've got that pole going on. So when I go to write my domain, I have to exclude -3 and I have to exclude 1. So this is what it looks like to exclude -3. And this is what it looks like to exclude +1. Very good. Now, looking at the photo, can you tell what the range is going to be for this function? What?
-infinity is 0, 0 to infinity.
Yes, you're right. So the only y value that I can't get to with this curve is 0. Right? I can get everything else up to infinity, down to -infinity. The only thing I can't quite reach is the 0. So again, you're right with the range. It would be this. Okay? You don't have to know what the sine function is for this class. Maybe you saw it in an earlier geometry class that you took. But you don't have to know this. I only include it because I might show you a picture of it. And you should be able to look at a picture and infer stuff. What does it seem like the domain is? Yeah, this just repeats itself over and over and over. And what does it look like the range is on this thing?
1 to -1.
Yeah, exactly. So, again, you don't have to know it. I'll just give you a picture if I choose to use any kind of bizarre, exotic-looking functions. But in this case, the domain appeared as though it would go from all real numbers, and it does. And the range here goes from -1 to +1. I say that because just looking at the picture, I can tell that the lowest this function ever goes is -1, and the highest it ever goes is +1. All right, one more, and we'll move on. What does it look like the domain is? Yeah, and what does the range look like? Yeah, 0 to 1. All the y values are stuck between 0 and 1. Very good. All right, so this is a long list, but these words I think are very intuitive. Maybe we've even mentioned some of these before in class, but we say a function is increasing if it goes up from left to right. We say that a function is decreasing if it goes down from left to right. We say that a function is constant if it is flat horizontal lines. We say that a function is strictly increasing if it is increasing at every point in its domain. Likewise, we say a function is strictly decreasing if it is decreasing at every point in its domain. A local maximum is just a point that is greater than its immediate neighborhood. A local minimum is just a point that's less than its immediate neighborhood. So there's a local maximum and there's a local minimum. But an absolute maximum is a point that is the very greatest point in the function. And likewise, an absolute minimum is the point that's the very lowest value you can get from the function. So I don't expect you to copy all of this down. Don't give yourself a hand cramp. But are there any questions about what these words mean? I'm also going to show you examples. And so we'll describe these examples using those words. If I've got the function 3 to the power of negative x squared, this is a function where it's increasing, and then it reaches a absolute maximum, and then it's decreasing again. If I have the function y equals x squared, this is a function that's decreasing, and then it reaches an absolute minimum, and then it's increasing again. If I've got the function negative 2 to the power x, this is a function that is strictly decreasing. And there's no maximums or minimums because it's always going down from left to right. If I've got the function x cubed minus 3x, this is a function that's increasing, and then it reaches just a local maximum because there's higher points than that. And then it decreases and it reaches a local minimum because there's actually lower points than that. And then it's increasing again. So this function doesn't have an absolute maximum, it doesn't have an absolute minimum, but it does have local max and min. And then we've seen that one, and the only one we haven't seen is this. This function is an example of a function that is constant, yeah, strictly constant. It's flat everywhere you look. So that's where you would say it's constant. I might ask something like this. Maybe not every single question, but maybe some of these questions on a test. These are really, really, really easy if you know the right notation to use, If you're familiar with interval notation and you know when to use coordinate pairs and when to use intervals. If I ask for the domain, I'm thinking about the x values. And to me, if I see these little arrowheads, the arrowhead means it keeps going. I'm not going to keep drawing it because you run out of paper, but the arrowhead means it keeps going up to the left and it keeps going up to the right. So let's say the domain is all real numbers, and this is an interval along the x-axis. Okay. When I say the range is going to be expressed in terms of an interval along the y-axis. So think about the y values. And the smallest y value I can get looks like it's somewhere around here. It happens at this absolute minimum. And that absolute minimum has a coordinate pair that looks like maybe negative 0.6 comma negative 1.7. I'm just guessing. It doesn't have to be super accurate. Just put down a number that's close. And that means for the range of f, I might write like negative 1.7 up to plus infinity. And again, keep in mind, when I write the absolute minimum, this absolute minimum, that's a point in my xy plane. And so I'm going to write a coordinate pair. That means the first number is an x coordinate and the second number is a y coordinate. But when I write the range, that's an interval. And so both of those numbers are places along the y-axis. They're not a coordinate pair. That's what I mean by using context clues. They look the same, but you got to know which is which. If I wanted the intervals over which my function is increasing, I would say this function looks like it's increasing between negative 0.6 and positive 0.3. And it's also increasing from positive 1.3 probably up to infinity, as far as I can tell. And again, I'm asking for an interval. So you expect this to be interval notation. And this is always in terms of your x value, never in terms of your y value. The only y-valued interval that you'll ever write is the range. But domain is in terms of x values. The interval over which you're increasing or decreasing, this is in terms of x values. I shouldn't use confusing symbols. Decreasing, same thing. I want to know the x values where this function is decreasing. And so I might write the decreasing intervals like this. So places where my function is going down from left to right in terms of x valued intervals. Does f have any local maxima? Yeah. And I might identify the local maxima by a coordinate pair, because that's a point on the plane. And so that maximum looks like it's at the point 0.3 comma 0.4, whereas 0.4 is the y coordinate here. Does it have local minima? Yeah. There's a local minimum at the point 1.3 comma negative 0.1. Does it have an absolute maximum? No. And yeah, I already put the absolute minimum on the graph right here. So, to recap, this is a very easy question. You don't even have to get the numbers precisely, right. If you put down negative 0.6 and the real answer is negative 0.7, who cares? Full credit. You don't miss any points. But what you do need to know is domain is always an x-valued interval. Range is always a y-valued interval. Intervals of increasing and decreasing only talk about the x values along the intervals. Intervals along the x. But if I ask you for places where there's a local maximum, local minimum, absolute max, absolute minimum, you should use coordinate pairs. So you have the x coordinate comma the y coordinate. That's the only possible confusion, right, with this kind of question. But it'll be multiple choice, and maybe the multiple choices will help you out. You can eliminate answers, get everything straight. Okay, almost done today. We say a function is continuous if you can draw the whole curve without lifting your pencil. The sine function we saw earlier, this is just a wavy wave that goes on forever, and of course I can draw that without lifting my pen. This function is the rational function with a pole at x equals 0, so it looks like that. That obviously has a discontinuity, and this function is the one that's constant or flat, except for the jump discontinuity. So that has a discontinuity right here. Now a piecewise function. A piecewise function is any function that's defined in two or more pieces. This is a piecewise function. The first piece says that the function value is x squared if x is less than 0. And the second piece says the value of my function is negative x if x is greater than or equal to 0. So I've taken my domain and I've split it into a first piece and a second piece. And I need to determine whether or not this is continuous. So one thing you can do if you have technology available, is I can just plug this into Desmos to see what the function would look like. And the way you do this is I say, my function is x squared if x is less than 0. Oops, that's not right. You put that there. Hot. So, I'll make it blue. And then it's negative x if x is greater than 0. I'm going to change colors too so you can see the difference. On Desmos, the if statement is with the curly brackets, you know? And so that says x squared if x is less than 0, and you can see the first piece is in blue, the second piece is in red, and you can say, okay, is this continuous? Yeah, you can draw this whole thing without ever picking up your pencil, so it's continuous. And what do you do on your test? Right? Like if you're taking your test and you don't have Desmos, because you can't just pull out your phone and do it, all you have to do is ask, do these two pieces have the same value at the trying to think of what's the best way, the best word to use here. At the transition, at the trade-off, at the, what I think about is Olympic relay races. You've got one runner that runs a lap and then he passes the baton to the next runner. And so I think about this as the place where they hand off the baton. So in this case, my first piece has the whole function and it's running with it until it hands off the baton to the second piece, and the location is x equals 0, right? I go from x less than 0 to x greater than or equal to 0 at the point x equals 0. And there, the first piece says x squared, that would be 0 squared, and that would be 0. The second piece says negative x, that would be negative 0, which is 0. And these have the same value. And if they have the same value, then the function is going to be continuous. Where the first piece passes off the baton to the second piece, if they've got the same value, then it's a continuous function. They met up at the right spot. Okay. Another way you can see a piecewise function is like this. I've got 3 pieces this time, and that means there's 2 places where we have to pass the baton. The first baton, as it's passed from the first piece to the second piece, that handoff happens at x equals 0 again. And so the first piece is 0 cubed, because the first piece looks like x cubed, so that's 0 cubed, that's 0. The second piece is the square root of x, and so we're talking about the square root of 0, which is 0, and these are the same. So I know where the first piece and the second piece pass the baton, they're going to meet up, they're going to be continuous. But there's another place where this happens, going from the second piece to the third piece, and the handoff happens where x equals 4. And so the second piece is the square root of x, so we're talking about the square root of 4, which is 2. The third piece is negative x, which is negative 4. And these are not the same. And so this function is not continuous. There's a discontinuity between the second piece and the third piece. So let me say it's x cubed if x is less than 0. It's square root x if x is between 0 and 4. And the function is negative x if x is greater than 4. And so this is what it looks like graphed. We go from the first piece to the second piece seamlessly. Very nice and continuous. But then the second piece to the third piece is where we drop the time. It's not continuous. Okay, now I also could have you evaluate piecewise functions. And so if this is my function f of x, what is f of 2? So f of 2, that just means I rewrite my whole function, but I replace all of the x's with 2's. So this is equal to 2 squared if 2 is less than 0, and it's equal to negative 2 if 2 is greater than or equal to 0. Is 2 less than 0? No. So the first line is nonsense. I don't have to worry about that at all, because 2 is clearly greater than or equal to 0, and so the value of my function is negative 2. Okay, next one. If I want f of negative 5, again, just rewrite your function, but replace all of the x's with negative 5's. Is negative 5 greater than or equal to 0? No. So the second part is useless. I only have to worry about the first part, where negative 5 is less than 0. And that means my function value is negative 5 squared, which is positive 25. Okay. This part, f of 0. That's 0 squared if 0 is less than 0. And it's negative 0 if 0 is greater than or equal to 0. And it turns out it doesn't really matter, but technically the right piece to choose is the second piece, where we say 0 is equal to 0. And so the right answer is negative 0, so it's 0. F of 0 is 0 in this case. So evaluating piecewise functions, there's nothing new or crazy about it. What about g of negative 3? I'm just going to rewrite my whole g function, but I say it's negative 3 cubed if negative 3 is less than 0. It would be square root of negative 3 if 0 is less than or equal to negative 3, less than 4. But 0 is not less than or equal to negative 3, so I don't have to worry about the second piece. Is negative 3 greater than or equal to 4? No, so I don't have to worry about the third piece. The answer is negative 27. Right? We just choose the piece that matches. Here's a trickier question. And then I'll see what you think. If I want g of 4, which piece do I use? The second piece or the third piece? The third piece. The second piece is only used if x is less than 4, but it's not less than 4, it is 4. I have to use the third piece because it works if x is greater than or equal to 4. And so the right answer is negative 4. If you accidentally used the second piece, then you'd be out of luck because you would have written down 2, and that's not the right answer. The right answer is negative 4. So make sure you're using the right piece of the function. Maybe you're aware of this, but there's only one place in real life where you use a piecewise function. Happens once a year. in April. This is a screenshot of the IRS Form 1040 instructions where you calculate your taxes owed based on your taxable income. And I want to point out that this is really a piecewise function. It's got 4 pieces to it, and the first piece says basically your taxes are 0.24x minus 6,600 if your amount of taxable income is between 100,000 and 182,100. The second line of this table says that your taxes that you owe is 0.32x minus 21,168 if your taxable income is between 182,100 and 231,250. And there's 2 more pieces to this function as given in the table. But these pieces in this function, this is what people call tax brackets. And it's a kind of a common misconception that people generally might be confused. I mean, I know one person at least who's confused by this, because I was sitting, at a bar like 2 months ago with this guy who was telling me he was done working overtime, because he said, every time I work overtime, it increases my annual income, but that's going to push me up into the next tax bracket. And he was afraid of reaching some point where he earned like $5 more of income and then had to pay $5,000 more taxes. That's what he was telling me. He was convinced that this piecewise function that determines your taxes, he thought it was discontinuous. He thought tax brackets just jumped you up from one piece to the next. But if you actually take the time to graph this on Desmos, you have to zoom way out because these are big numbers. So you zoom, zoom, zoom out. You'll see that this is 4 different line segments, but they all connect, right? This is a continuous piecewise function where one end meets the other end, and it meets the other end, and it meets the other end. And so when you have these tax brackets, what it really looks like graphed is something like this. And I'm exaggerating so that you can see the difference. But every time you go up a tax bracket, the slope gets a little bit steeper, going from one piece to the next, because people who have higher incomes pay a higher tax rate. But there's never a point where your taxes just jump up and, $1 to the next. You don't end up paying an extra $1,000. It's